Alright, today we're going to look at the Fibonacci sequence, which is a group of numbers that goes something like this and on as long as you want. In order to make one, all you do is turn two numbers, add them up to the next. Two numbers, add them up to the next. And for any number, you just add up the two previous to get it. This means it's going to grow really quickly, and after a few more, it'll be in the hundreds and thousands and so on. This was introduced by a guy named Fibonacci in the same book when he introduced Arabic numerals to Europe. They were using Roman numerals before that, which are fine for normal counting, but are not very good for certain types of math. And Fibonacci used the example of rabbit population growth, where if you have a certain amount, they'll grow more and more each generation. But this sequence shows up in all kinds of natural phenomena, spirals and shells and flowers and so on. In the code to make it, it seems so easy. Let's make a function called fib, so we don't have to type his long name. And if you want to say fib of n is fib of n minus 1 plus fib of n minus 2, that means if you're going to get the seventh thing, you just take the sixth and the fifth and add them up and get it. That means we have to start with something. So we're going to say if it's less than 2, we want to return 0 if it's 0 or 1 if it's 1, so we can return n. So this is all we need, and it looks really simple, but unfortunately it's not. Here's what happens. For I in range 20, print fib of I. That's going to go down the line and give us all our Fibonacci numbers, and it looks okay. It's giving us the right sequence, and it keeps going. But imagine we wanted a lot. Sometimes you want a lot. This is used in finding all kinds of interesting sequences and has properties related to prime numbers and stuff. Maybe you wanted to go 200. Well, that's not going to happen because it slows to a crawl after not that many. This is only like 30-ish, where it's taking a long time for each one, and pretty soon it's going to freeze and not complete the job. Even if it didn't freeze, it would take a month at this pace because it's getting worse every time. So let's think about why. This is written as a function that calls itself, which is something we refer to as a recursive function. And sometimes people describe those in sort of magical terms, like they're this strange thing that defies all laws, but really recursive functions are totally normal, and you could rewrite it to be non-recursive. But they're so nice when you look at it and you understand what this means, because this is the way we think. If you're looking at the list, you think, okay, 10, 946 equals this plus this. It involves looking at the list to make more of the list, right? However, the problem is the computer isn't doing that. It's not looking at a list and using those because it doesn't have that. It's doing the work every time, multiple times. So when it found 6765 and then it went to the next one, it had to find 6765 again to use it as part of this guy. And to find that, it had to find this and this and this and this all down the line. So every time we get to one, it's doing the work all of the previous ones needed again, because it's not remembering its previous answers. So we want to change that. We want to tell it to remember what it's done so it can instantly use it in the next guy. How do we do that? Well, sometimes processors will involve some amount of caching on their own, and they'll remember what they've done and use it if it comes up soon. Sometimes you can import modules that'll do this for you, but let's say we want to do it on our own. at least once to practice the idea. And as I said, this idea is called caching. When you do some work and you think you might need to do it again soon, you remember it so that you'll save yourself the trouble. If this happens in a computer, it sounds like some fancy thing, but this happens in your brain all the time. If you remember somebody's phone number and then 2 minutes later you need to type it in again, well, you remember it in your short-term memory and you don't have to look it up the way you did the first time. If you do some math that involves finding the square root of 423 and then a couple lines later in that same math problem you have to find the square root of 423 again, you don't start from scratch. You don't do the math or get out your calculator. You just say, hey, I wrote that 2 lines ago. I'll copy it from there. So this is going to involve the thing we've been talking about all quarter, which is a dictionary. We're going to put our stuff in a dictionary, and then if we ever need to find them, that's where it'll be. Let's do that. We want to say there's a fib cache that equals 2 curly brackets, or some people call them braces. And we could start it blank and then add it when we do these. Or we could start it with 0 and 1 to save us the trouble of this line, and we can cut out this line. Now we need to say, okay, if our thing is in the fib cache, we use it. If not, we calculate it. If not in fib cache, we do some stuff, which will be kind of like that. Otherwise, we return the answer from the cache. So if it asks you to find Fibonacci 1, well, it's right here. You don't have to do any math at all. You already figured it out. So if we were going to calculate this, we're going to say some variable. I'll call it num. And num equals probably something like this. And then we add that to our cache again. So if our number is not in the cache, we find it and then add it, and then whether it was or not, we take it out of there. So the second will be added, the third will be added, and then we can use those in future versions, meaning it doesn't have to do all the work every time. It just has to do one addition problem every time. Add these to get that. Add these to get that. Add these to get that. So let's hit run and see how different that is. Now let's hit run. It did it faster than we could even notice. Okay? It found all these and all these and all these. And it didn't take that much time at all. Because computers are totally fine to add big numbers. If you tell it to add that and that, they can do the job just fine. Because who cares? It's just addition. It's not like 100 layers of addition going back through the past and redoing work you've already done. So what I want to ask you guys to do is to use this same idea with another function. Okay? You don't have to write the code for the Fibonacci because I just did. But I want you to use this for another function that has the same property. It's also recursive. This applies to more than just recursive functions, but they're so nice and easy to read and easy to describe that I thought it would work. And I want you guys to do this with the factorial. The factorial is probably something you've seen in math class, and it's written with a exclamation mark. So 5 factorial equals 5 times 4 times 3 times 2 times 1, although you really don't need the times 1. And it's used a lot when you're finding how many ways a thing can be ordered, what's called permutations. So if you have 5 playing cards, then and you're putting them in a list, well, the first one you have 5 choices. The second one you have 4 left, so 4 could go in that slot, and so on all down the line. The thing about a factorial is that you can take the previous one and build off of it. So 5 factorial is just 5 times 4 factorial, which is just 4 times 3 factorial, which is just 3 times 2 factorial, and so on. And this is obviously useful if you're going to do a bunch of them. If you're going to find 5 and then later you're going to find 7, well, you can use all the work that was already done for 5 and just add a tiny bit more. And if you're going to do big numbers like 200 and then 212, well, saving that work from the first time might be nice the second time. This means that you're going to do a very similar thing to what we showed here, except with a different core mathy part right in there. I want you guys to write a function that does the factorials all the way up to, let's say, 200. And it should go fast like this instead of going slow and crashing and stopping and running out of space like it did the first time I tried. Let's see how that goes. Thanks.